So today we are going to continue from the RDDs, basics of RDD. And where did we leave yesterday was at the point where we were trying to write a function which could compute the random sample of your data, right? So why do we generally need a random sample? Anybody? All right. The question is here, we are trying to create a random sample of a data set. Let's say you have few gigabyte of data, and you want, say, 500 records out of these millions of records. So you want a random sample. So what's the use of a random sample? What's a real practical use of a random sample? Right. Thank you, Gerald. It's easier to create statistics from, to capture visibility, right? Michelle's point is to get a general view of what will happen in the whole data set. Yes. Great. Great. So before we had the big data point, big data tools, what we generally did was we took a sample, or we conducted the sampling exercises out of humongous data, and then we based our statistics on that sample set. Okay. Now, in today's world, having the random sample is very important. Why? Let's say you wrote a program, you are trying to build a Spark program. So instead of right away testing your program on terabytes of data, you would want to test your program on a smaller data, right? And on a smaller data, if you just take first few records or last few records, that may not be the representative of actual data, right? A better way to do is pick some random records out of the whole data, and on the top of it, we do the testing. Okay, we do the testing. All right. Now, to facilitate that kind of thing, Spark RDD provides a method called sample. Okay. Now here we are trying to create one such method. Okay. So the objective of the exercise is to pick a random sample from a huge data, though there is a method provided in RDD, but we are going to create our own. All right. So it's a real use case of something what we have learned recently. And it's very simple. Can somebody suggest an approach right now? How, whatever knowledge we have so far, can we use that knowledge in order to generate a random sample? Can we use map, filter, flat map, or reduce, or those functions like take or collect to compute the random sample? Right. But how? Can you suggest an approach? Anil, Ganesh, Gaurav, Gerald. Let's say you have a huge RDD containing billions of records and you want to compute a sample of it. You want to just find out, say, 0.1% of total records. Okay, 0.01% or 0.1% of the total records. What will you do? Okay, so Gerald says we could use map. Anybody else? These are important exercises, so please work with me on these. It's going to help you in many ways. Okay, so if you use map, you cannot skip, right? TJ says that break the Hughes data into parallel RDDs. Okay, that's actually the definition of RDD. And then return one value from each. Okay, and with filter, take, collect, map, or flat map, which function can we use to do that? Which one? The question is which one? Very good question from Anil. What's the definition of random sample? Random sample means this sample that we are picking should be uh, from different locations in the data, not only say in the beginning of the data or in the end of the data or all of the records in somewhere in the middle. The sample that you pick should be from the entire distribution. Okay. It should be like some record, first one, third one, then 90th one, then 100th one, then 1000th one, and so on, right? That's our definition. Najib says that we could use flat map or filter. Good. Okay, Gaurav says take and collect will give you the first few record if we use directly. Flat map might work and then use collect. But how will we do the random part? Yes. Mm-hmm. IDK as in? Okay. Ganesh says that from first principles, simply generate a random value and filter an attribute based on the random number. Wonderful, wonderful. Thank you, Michelle and Gerald. Okay, looks like I'm poor at the acronyms yet. Uh, All right. All right. And okay. Or you can say that it's a little difficult to decipher the question so quickly. All right. Now, yes, so we are going to follow the approach suggested by Gaurav, Ganesh, and Najib. So what we are going to do is something on those similar lines. Okay. So let's say, okay, let me simplify the question. Let me simplify the question. Out of all the records, if we have to just pick random 50% record, it's not like first 50 or last 50%. If it has been first 50, we could have done take, right? But we want a random 50%. How would you do random 50% of the total records? How can we pick random 50% records? Anybody? Yes, there is a random function in Scala. And this random function generally returns a value between 0 to 1. A random decimal value from 0 to 1. Gerald says use a randomizer. Okay. All right. All right. Now here is the idea. Okay. So let's try to first solve it to pick 50% record. The approach is very simple. We pick a record from RDD and do a coin toss. If it's head, keep the element, otherwise discard it. Right? Can't this be achieved using filter? So if you write a filter function, what it does is it throws a random coin toss. And if it's head, then it let it pass. So the chances are the result will be about 50%, but not exactly 50%, right? We are basing the things that if we throw a coin, there are 50% chances of head. Therefore, in 50% of the cases, this filter will let the records go in 50% cases. But that's just assumption. It could be little more than 50% or little less than 50%, right? Is the approach clear? So in the filter function, what we are going to do is we are going to throw the coin or generate a random number between head and tail. If it's head, we let it pass. Or you could do the same thing with if it's tail, let it pass. Okay. All right. Now, let's say we have to pick instead of 50%, we have to pick 1/6 elements, right? 1/6 element. So what we'll do is, in that case, we will throw a dice with 6 faces, right? And if it's 1, then let it pass, otherwise stop it, right? Similarly, we could do other things. And so in case of computers, we can create a random function which can behave like um, coin with hundreds of faces. Okay. And of course, it would not give the exact size. Is the approach clear to everyone? Anil, Ganesh, Gaurav, Gerald, Isha, Michelle, Najib, TJ. Please feel free to ask. This is an important point to ask. Okay. If I have to interview somebody on the big data, specifically into data engineer part, I'll ask some deviation of this question or the average question. Okay, and that's what people have been asking. A lot of people keep on, I see on our forum, people posting questions similar to this one. And that's why I decided to create this example for you. Okay. Now, uh, all right. So since this time we have expanded many topics in Spark, so you might have to bear with me because the time might go more than what we had expected. All right. But I want to make sure that all of us learn what we plan to learn. Okay. A question from Ganesh is, but in this approach, we have to iterate over all elements. And right? Not really, not really. Inside filter function, we will give our coin toss and let the filter function decide. Okay? And that filter function will run parallelly on multiple machines and will let some records go or and some records not go. Okay? So that's one approach that we're going to follow. Question from Robert, is it possible to reach an RDD object as an array? Good point, but that'll be basically um, converting that into a local array, and that might hurt the entire logic. Okay, right? That's why we would like to avoid all the logic in which we tend to use a for loop or some other algorithm which needs entire array together on the local machine, right? We will try to change our way of thinking. It's hard, but we'll try our best to slowly move to thinking in a distributed way, thinking in a divide and conquer way. Okay, so all right, here's an approach from Anil's side. Generate tuples with key and value, where key as the position and value as a sample, key as a position and value as a sample. Save this as RDD and use a random number 0 to 1, create 50 records within 0 to 1 and multiply each with 50 and round it as integers. All right, pass each integers to filter function and get the tuples matched. Okay, all right, all right. I think half of your approach is extra, and half of the approach is something which is sufficient. All right, you will see that now. Uh, Okay, I think I got it, what you're trying to do. All right. Great, great. Very good set of answers. And all right. So here we go. So first of all, let's say we have an RDD of numbers. It could be RDD of names, RDD of strings, RDD of object. It could be anything. Okay. Now let's say we want in the output we want a fraction, like we want 0.1, right? 0.1 means 10%. Okay. Had it been 0.2, that means 20%. Okay. So if there are in input, there are 1,000 records. We need 100 random records. That's what the fraction represents here. So what we do is we define a function called coin toss. Okay, and there we define what we do is we call the random number generator, right? Random number generator. If this random number generator is less than fraction, okay, then we keep those records. Otherwise, less than or equal to fraction, we keep the record. Otherwise, we discard it. All right. So that way, the chance of a number coming less than fraction out of something between 0 and 1 is equal to the fraction, right? So that's why this function should work fine. Does it make sense? So if we had a dice of 6 faces and we are saying give us 1/6 record, then what we'll do is if the value of the face is lesser than or equal to 1, that means let the record pass, otherwise keep it, right? So that's what we are doing here. And so if you run this coin toss function, it could return true or false randomly. Okay, this coin toss function could return true or false randomly, and it would return 1/10 time true, and rest of the time it will return false. If you called coin toss 10 times, the chances are you will get true only once. Okay, does it make sense to you? Now, what we are doing is we are saying rdd.filter and passing this function as argument. So this RDD would be having the random sample of this fraction, this size, okay, 0.1 times the total RDD. If total RDD has 100 records, we would get 10 records in the output, okay? This is the case where everybody's answer will be different. If we try to run it on the cluster, all of us will get different results. I can show you. And every time I execute this function called collect, I will get different results, okay? All right. So is it clear to everyone? Yes, it will be like throwing a die with 10 faces. Thank you. All right. Now let me just launch Spark Shell and then take a look at it. Is the approach clear to everyone? A question from Anil. If the fraction, why is the fraction 0.1? If we want 50%, then in that case, we'll just change this to 0.5, okay? We can read this as the argument of the program, okay? And we can use that way. Good question. All right. So let me just show you. We created an RDD having 1 to 1,000 records. Okay. So then we defined a fraction 0.1. Then we defined a function called coin toss. Here we are defining a function called coin toss in Scala. Here we are saying that the argument to this function is an integer with the name x. It returns true or false, right? And then we are comparing this number with a fraction. Okay. Next, what we are doing is that we're calling this function with filter. What will it do? If this coin toss returns true, that particular record will be kept. Otherwise, it will let it go. That's right. All right. So let me define the coin toss. It returns a boolean. Did I say something else? Okay. So define, yeah. All right. Okay. So this function called coin toss, okay, if you see, let's say we are passing the fraction. Sorry, this is supposed to be, okay, this is, yeah. So actually it's not using the x value at all, okay? So whatever is the x value doesn't matter. So now it's giving false, 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 once it has come true. Do you see? Approximately 1 in 10 times we got true. Now it makes sense to you? Okay. A question from Robert. Coin toss returns Boolean. Filter Boolean will keep it versus leave it. Yes. So when we say filter, right? So for every record, coin toss will happen, right? This function will be executed. If this coin toss says true, then it will keep it. Otherwise, it will leave it. Here we are passing the filter coin toss. It's a function that we are passing, okay? Not the value, not Boolean. We're passing the coin toss. All right, good. These are good doubts to have, okay? And all right, is it clear to everyone? How will it work? So the meaning of coin toss everybody got. This is some value of RDD which doesn't matter for coin toss, okay, which does not matter because a coin toss has to be unbiased. No matter who is the party, it should behave unbiased with it. Therefore, it does not use the past value. Okay. So again, now what happens is here we are saying this is our actual RDD and filter with coin toss. Okay. So against every record, coin toss will be called. If coin toss returns true, then that value will be kept. Otherwise, it will be given out. It will be discarded. Okay. Now, when we say collect, all of the remaining records will come locally, right? Now, I'll show you the length of this. You can see there are 101 records. Do you see that? For some, it could be 89. Or for some, this time I got 98. Okay. 89 is an interesting number. I never got 89. Okay, so if I keep executing, this time I got 89, 98, 102, 115, 99. All right, this is interesting. Okay. A question from Michelle. In real life, will you save these records to a file? Generally, yes. So it depends on what we are trying to do. Here we want to use them locally. Let's say there is a statistics function which want to test against the sample data. So we could use the local one, or ideally we should be saving it in HDFS so that we can run our test program. We can test our program against this local sample, small sample. Instead of saying collect, we will say save as text file, and that will save in HDFS. Okay, wonderful. All right. So is this example clear to everyone? It's a very simple example using very basic functions. A question from Robert. The argument for coin toss is assumed here. I understand that it's not being used, but when being called, should we not call it with an integer? Okay, that's a good point. So what he's saying that when we are calling here, right, when we are passing here, should we call this? No, because filter's job is this filter function that you see. That is what it does is it's going to take every element of RDD, partition, and call this function against that value. That's the job of filter. All right. Yes, the signature of any function that is passed to an RDD, any function that is passed to an RDD must have the same argument type as the RDD's data type. Okay, RDD contains integers, and therefore your function, whichever you are handing over, this is a pointer to your function that you're handing over to the filter. Pointer as in it's a reference, it's a link, you are handing over your code to filter function. Okay, this filter function must have this function what you are passing here must take the same type of argument as the data type of the value stored in your RDD. Okay. Did I make sense, Robert? I would love to understand your question more. All right. Yes, I can unmute you for a moment. Go ahead.
Sandeep, my question is the definition says coin toss of integer, right? When we
Right.
pass the RDD.filter, you don't say RDD.filter.coin toss of some number, random number, right? Meaning, or one or two or whatever.
Do you mean
Not that,
do you
right?
mean okay,
No,
okay.
not that.
Do you mean we are not passing fraction?
No, not that. I understand that. I understand that the fraction is used in the coin toss implementation. My question is, the coin toss itself has got the integer data type.
Right.
So when you use the coin toss function within that like wherever you highlighted, I would ideally expect that it says that coin toss of 1 or 10 or whatever, just for the sake of the signature to be, you know.
I see. I see. I see. So yes, so generally what we did earlier in case of Python, Java and all, we generally created an object of an interface and handed it over there, right? Here we hand over the signature, and the signature of a function holds the data type of the argument internally and the return values data type along with the body. Okay, so the signature is sufficient to inform filter that it is going to it is having this argument like this. Okay, so this is how we generally define something in Scala, like we define a function, and while handing over we don't need to define pass extra value like what is the data type of the argument here. Is
So
that clear?
the X will be replaced by the values of the RDD internally.
Yes. So if you think about this filter function, right? If I had to write Spark again, it would look like this. I'll show you. I'll try to show you. Okay. It's a very important question and it sometimes causes confusion. So if I had to define a filter function, I'll define like this. Filter, let's say the function being passed and it returns say RDD, and I'm just trying to uh, show you like if I am writing Spark, this is what I'll do, right? What I'll do is for here there is a RDD that's being returned and there is an internal RDD for X value, right? In the RDD dot partition or let's say just RDDs, okay? for x in RDD, right? I'm going to call this function with x. This is what filter does. Sorry. What it does is, if, okay, if function is this, then yield. Okay, that's what it does. Yield means create a vector and return that. So basically, if the function, when this f called on a particular value of an RDD, if that's true, then it will give the results. Or let me just create, let's say, where output equals new RDD. And here what we are doing is, I'm just taking very hypothetical case. Okay, we are saying output dot add, what's that? Like this. All right, don't worry, I'll just explain my idea, and then I'll say X. Okay, in the end, I will return output. So this is how a filter function would be behaving internally. Great. All right. A question from Najib. Question from Najib is that, is there an occasion while using Spark where a for or when control structure is used? You will see that there are situations where it will be used. For example, let's say you're trying to operate on partition by partition. In those cases, you can use a for loop, you can use some other kind of loop. All right. So based on the problem, you will understand. A question from Robert. In case by mistake I passed a function that has 3 arguments into a filter, will it be able to be a compile time problem? Yes, it will throw a compile time error. You can try experimenting. So here, if we define a function here, let's say we defined a function without an argument. Okay, we defined a, let me just try to define the function without the argument. Okay, sorry. All right. These are important questions. Okay, we should not be ignoring these. All right. So here we have defined a function called coin toss without the argument. But the moment we are going to pass it to this, it says that found this, meaning it is taking no argument, right? Required something that takes integer and returns Boolean. Okay. All right. Great. All right, so that was pretty much about the very basics of RDD. We are going to take a little more operations further, okay, on simple RDDs. Then we are going to go with key value, and then we will do an end-to-end application, okay? We're going to do an end-to-end application after this. All right. Quick check to everybody. Is everybody paying attention? Are you finishing the, if you go into, say, my courses here, if you go into my courses, are you finishing the self-paced course parallelly? This one? Are you finishing it? All right. All right. Okay. So these 3 points that we have left so that we can do it together with other people in the Scala session. Okay. These things also you can give it a shot. All right. So that you are ready with your doubts and questions. Okay. These 3. All right. And please try to finish it. It will be very important. It will be very useful. And you will be able to learn a lot if you just go through these sessions quickly And in case you know it already, mark as done and keep moving. Okay. So next time we are going to work on writing Spark applications. All right. Though the order is higher, but since people are asking it earlier, so we are going to move it a little earlier. So Najib cannot see those are actually. Let me make a note. Thank you, Najib. I will I will get it checked. Okay. So maybe there is some permissioning issue. All right. So inside Spark and Scala, do you see these topics from here, from this point onwards? I see. I see. I'll have to take a look. You see only this and one more, right? There is a Spark here and there is this. Okay. Right. So actually, those who had taken the Spark as in Hadoop course as well, they will see the entire Zookeeper yarn etc. And okay, that's one thing. Okay, now coming back to it. So do you see this one, Spark developer course? Ouch, not this one. Najib and Anil, do you see this one in your My Courses? Okay. All right, I'll take a look at how it looks. I'll try to change the roles for myself and we'll give the same rules as yours and then test it. Okay, Anil, and let me just make a note of it. All right, test Anil and Najib's accounts. All right, good. Thank you for reminding this. All right, so what we learned so far is that using basics of RDD, we were able to do distributed computing without much of computing because most of the headache of moving code between machines, taking care of failures, taking care of distribution of data, everything is done by Apache Spark for you, right? And only thing you need to do is you need to load the data into an RDD, then run the functions on top of RDD. As long as you are running the function, running your logic using the constructs provided in RDD in a parallel way, your data will be distributed, and chances are that you will be able to do a lot of high-end programming. Okay, lot of heavyweight lifting can be done using whatever we have learned so far. All right, so this is the true power of Spark, that we were able to quickly do the random sample with a very simple function without having to write too much of code, without having to compile it, creating packages, submitting it. We were just able to do it interactively like a data scientist would do, and it would, like a data scientist would examine that data in the real time. Okay, so that's what we have demonstrated so far. All right, now let's take a few more examples of basics of RDD. Okay, so basics of RDD provides implicitly a function called sample, right? The one which we just created, it's there already in the RDD. Okay, what it does is it takes a fraction as argument. Okay, and to further make it truly random, you can provide a seed, which is not really required by default. Seed is the current time. When you are generating random number is never real random. It's always a pseudo random. To make it more and more random, you generally provide a seed. Seed is a completely random number, and That seed could be anything. It could be the sound that your laptop is receiving or computer is receiving, or how much hard disk is left on your machine, or a combination of many parameters which could vary between many computers. Okay, so creating truly random is hard in computing. Therefore, a seed is created so that you can generate seed, and rest of the random number is taken care by the system. All right. Now, and with replacement means if this is turned on, it will let it duplicate the records. Okay. Otherwise, it would not let it duplicate the records. Okay. So you see here, we have created an RDD called SEQ here, and by parallelizing these 100 numbers and creating 5 partitions, and then we are saying SEQ sample, and we are passing replacement as false and fraction as zero point 0.1. Here square brackets means that this is optional argument. Okay, and once we are done computing sample, then we are saying collect. Collect is bringing all of these records locally. Anil's question is that are we on the schedule? The quick answer is no. We are going with a little bit more details about RDD. All right, that's a general agenda. Okay, so don't worry about agenda. We'll take care of things. Don't worry about it. Okay, we are actually 2 sessions behind, so don't worry about it. All right, the next function we have map partitions. What does it do? It's a very important function. Please pay attention. So map partitions is like map, just that you get a partition, not a single record as argument. Okay, instead of operating on every value, you operate on a sub array, right? A huge data is generally is broken down into partitions. Partitions is like subset of total number of records, and every partition is generally executed by a single computer, and the way a partition is processed is sequential, not parallel. Okay, so the way partition is processed is always sequential, as in if you have 100 records in partition and you are computing reduce function, doing a reduce, then there will be 99 calls in a sequence on this partition. Okay, so computation of partition cannot be further parallelized. Partition is minimum unit of parallelization. Okay, so if you have, let me answer this way. Let's say there is an RDD. Let's say there is an RDD having 100 records. Okay, and 10 partitions. Okay, there's an RDD having 100 records and 10 partitions equally distributed. Okay, now if processing a record, okay, if function proc, process takes 1 second, all right, 1 second to process X, how much time rdd.map process will take? Okay, all right. This is what I wrote. All right. Question to all is, if there's an RDD having 100 records and 10 partitions, and it's equally distributed, and there is a function called process which takes x as argument and takes around 1 second to do the computation on x, how much time will rdd.map would take? Yes. That's right. That's right. It will take around 10 seconds, little more than 10 seconds. Thank you, Robert. The overhead of calling this and calling that, we are just ignoring it. So we can safely say here that it'll take around 10 seconds. Okay. Okay. Let me check. What if we had 200 records? 200 records, 10 partitions. How much time will it take now? So each partition would contain how many records? 20, right? That means these 20 records will be operated in sequence, which means each partition would take 20 seconds, right? Is this okay with everyone? And therefore, overall, since all these partitions, let's say in the best case scenario, all these partitions are distributed on multiple machines or one partition per CPU. Therefore, all these partitions are being operated in parallel. From 0 to 20 seconds, all partitions will be finishing, right? Therefore, overall, it'll take around 20 seconds. Good. Ganesh, are you with me on this? Good. Thank you, Michelle and Gaurav and Gerald and Robert. Great answer. All right. So yes. So is this clear to everyone? What does it mean? Question is that there is an RDD having 200 records and 10 partitions, which are equally distributed, meaning there will be 20 records on every partition. And there is a function called process, which takes 1 second to process, and we are calling this function. How much time will rdd.map actually would take? As in, when we call collect, then the map will get executed and it will take some time. How much time will that be? Correct. It'll take around 20 seconds. All right, great. Moving on. All right. Now the point is that since a partition is not being broken down into multiple threads, okay, multiple processes are not doing the, we are not further breaking down a partition such that it can be operated in parallel. Therefore, it is very important to be able to process entire partition by ourselves so that we can do an optimization. That imagine that we are say I'll say so imagine we are exporting data to the database, right? Exporting data to database from an RDD, right? So it will, For every record in our RDD, we create a database connection. What if we just create one database connection per partition, right? And save those records. So it's very important to be able to use map partition. And when I looked at the Spark's code under the hood, most of the functions are actually implemented using map partitions. For example, map is actually implemented using map partitions. Okay, so right, therefore it's important to learn map partitions. So we have map partitions where we can pass a function, and this function will be called on each partition. The argument provided to your function when while executing will be the entire partition. The vector or the list containing all the records in a partition. Imagine that we have an RDD and we are defining a function which takes iterator as argument, not vector, iterator as argument. What is iterator? Iterator is kind of a cursor. If you are from database background, it's kind of a cursor, or it's a pointer. It's a iterator is provided to you on most of the arrays or lists or collections or vector. Every collection is an iterable, and therefore you can iterate using iterator. All right, so iterator is a class, the base class for most of these, and we are provided with the iterator, which is essentially a pointer to the list contained in a partition. Okay, so we get this and we return an iterator. We get an iterator, we return an iterator. All right, so what we are doing here is we are computing summation. This function is computing summation. How we are doing that? We are defining a local variable sum and then checking if the iterator has next element. If it has, then we are adding sum with the next value from iterator, and then we are returning a list containing sum and the iterator. Okay, that means the value that's being returned from map partition is a single value, though it's in the form of iterator. This iterator contains a single value. We are creating a list with this sum. So this list will be having a single element, and then this iterator is essentially the iterator of this list. Okay, so what will this do? It will basically compute the summation of each partition. This will compute summation of each partition. So now I think that answers Najib's question, that will we ever used the for loop kind of construct? We will. You can see that. Are you with me? All right. Great. Now, another important aspect is important transformation is sort by function. Sort by function sorts the data based on the key. And where's the key? Key is provided by the argument function. This is called a key function. This function basically generates a key given the value of an RDD. The sort by function sorts an RDD using the key provided by this function. Okay, sorts means ordering, and basically here using this function's key, we are ordering the data. All right, we can define ascending true or false. We can also here, since sort by would create a new RDD, and this new RDD will have shuffling in them. What does it mean by shuffling? When we are ordering data between partitions, there would be a movement of data, right? Since some records which are in the end, towards the end, it will be copied to the beginning and some will be copied to the last. So sorting essentially have a movement of data. We call that shuffling phase. So sort by has a shuffling phase, and this shuffling phase is very processing intensive, right? And if you want to repartition, because anyway shuffling is happening at this point, if you want to repartition, this will be a great time to repartition. Meaning in the input data you had 20 partitions and now you want 10 partitions. So shuffling will be a great time because anyway the data movement is happening across the boundaries of a record, therefore boundaries of machines. Therefore, changing the partitions would be a good idea sometimes. Okay. So instead of explicitly saying that repartition my RDD, you can of course repartition RDD. Wait for a point where you are anyway shuffling the data. That point you can pass the number of partitions here, and that is a optimization. All right, that's an optimization. So okay, now most of such functions, most of such transformations on actions, which have most of the transformations, not actions, most of the transformations, such as sort by, have this argument called map partitions. Okay, this argument called map number of partitions, and this number of partitions is quite useful for optimization. All right, now going ahead, function is a function used to compute the sort key for each element, and then ascending is whether to sort in ascending order or descending order. The number of partitions is number of partitions to create. So imagine that you have this tuple. You see, you have this list of tuples. Each variable is a tuple containing a string and a number. And when we create an RDD, what will each element have in this RDD? In this RDD, what will each record have? Quickly, I think I've put all of you to sleep. Tuple, that's right. So it'll be a tuple, correct? Good, good. And when we say sort by, the sort by function, sort by needs us to pass a function as the argument. Here we are saying that for every element, key is first member variable of this tuple. X is a tuple, x dot underscore 1 means first value, that is this. So we are trying to sort by the first element of tuple, right? And once we are done, we will call collect and it'll give us the result in a sorted order. Does it make sense to you? All right. Now further, let's say the key function, this time we are providing this key function. What it does is this key function is returning underscore 2, meaning the second value of tuple. When this function is called on this, it returns 1. When it is called on this, it returns 2. When it's called on this, it returns 3, and therefore the values will be ordered based on this. Therefore A1, B2, and 1, 3, D4, and 2, 5 will be there. Okay. Further, if you want to sort by a function, we can simply sort like this. What's the difference between this and this? Okay. Yeah, I think this is clear. All right. So we learned 3 things today. One is sample, other is map partition, other is sort by. Right. Now there are these few more functions provided called pseudo set operations. Okay, pseudo set operations. Even though an RDD does not enforce that the element will be unique or distinct in our RDD, there's no constraint. You can have anything. But set operations are quite useful. Therefore, they have been provided on top of RDD, and you can utilize set operations on an RDD in order to do various in order to do distinct, in order to intersect, and so on. Good. Thank you, Anil. So that's a good use of sort by. Let's say we want to find out top 10 most popular words in our word count example, right? So what we can do is, as Anil has suggested, that we can pass the second argument of our result as the key in the key function, and we'll be able to sort the data based on the second value, and we can say descending equals false, uh, 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 ascending equals false, and it will basically do the descending, and you'll get the top those many records. All right. Or we pass the negative -1 into the number as the result, you will get the biggest one first. All right. Good, good. So let's say we want to find out the distinct words or distinct letters, right? The distinct numbers. We can use a distinct function provided by RDD. If you want to concatenate two RDDs, we can use union as specified earlier. If you want to subtract, if you want to find out the delta of the two RDDs, okay, one way is, the bad way of doing the same thing is bring this RDD locally, bring this one also locally, do collect on this, collect on that, and then create a new array by iterating over both the values collected locally, and then again create a RDD with the resulting one. That's the lame way of doing it. That that would basically mean that you don't want to know, you don't want to use Spark, or you don't know how to use Spark. Okay, so a better way would be that we do the we use the union in the previous example, or if you want to do subtract, we can simply do subtract. All right. The other way would be subtract, meaning all the values which are there in second RDD, the argument, they will be removed from RDD1. So from RDD1, the coffee, monkey, money, and kitty will be removed. Coffee, money, and kitty. Kitty is not there. Therefore, panda and tea will be left. Okay. Now, intersection means the values which are common to both. So what are the values common? Coffee is common in both. Good. And monkey is common, as in actually not common. Here it's money, it's monkey, but I think it's a typing mistake. It should have been monkey. Monkey and coffee is common in both. All right. Now, sometimes what we would like to do is we have, let's say, two RDDs, okay, and we want to generate all possible combinations of RDD. A question from Robert: what is that requires shuffling in the previous one? Okay, it requires shuffling, meaning the way intersection works is that it removes the duplicates. Okay, therefore it would actually sort the data and then subtract. Okay, because if you write a program to do the removal of any of these, how would you do it? Is take an element from, say, RDD2, scan through all of this, then take another element, scan through again, take another, then scan through. And what will happen there? That'll become n into n, those many combinations. Therefore, what Spark does is it sorts RDD2 and RDD1 and then removes the duplicates. That will be n log n. Okay, those many combinations. A question from Najib, that why it's called Why it's called pseudo? Because here we are saying RDD1 is a set, right? It's not really a set. It has duplicate values. Therefore, since RDD is not enforcing those constraints explicitly, therefore RDDs cannot be a set. Therefore, it's called a pseudo set. Question from Robert. So it'll be shuffled and processed. Yes, it'll be shuffled as in first ordered and then processed. Okay. Great. Now moving ahead. All right. A question from all of you. A question to all of you. If you had to implement this by yourself, how would you do it without using intersection? Can anybody think of a solution? How would you implement intersection without using intersection? Let's say you are only given a function called union to concatenate two RDDs. Can you use union to do intersection? All right. Yes, you are allowed to filter. Okay, I think that question will be valid when we talk about future use cases. Okay. So yes, we can use subtract actually, union and subtract. That's good. That's clever, Ganesh. Thank you. And a question from Najib is create a map of tuples with the name as key and then filter it through that. Create a map of tuples, okay, with the name as key, okay, and then filter it through that. Okay, okay. Yes, that can be done. As in, that's good only if your RDD is fitting into the memory, right? So you will collect and create a map out of that whole RDD, and then hand that map as to our filter function. The way we handed over the fraction to our filter function in coin toss. In the same way, we will hand over that map to the filter function and then do that. Right? That's what you're saying? Right. In that case, the only catch is that this RDD being really huge, it is going to overflow the memory. All right. So we have to be, cautious about that part. Next is Cartesian product. We have already talked. It basically generates for every record in this RDD, it generates a combination with the second one. So user one, the beta brand, and user two, Asha tea house, and user three, ritual, and so on. So user one will be combined with all three. User two will be combined with all three. User three will be combined all three. Therefore, there'll be total 9 records here. 3 into 3. Okay. Is Cartesian clear to you? Clear to you? User one beta brand and user one Asha tea house, user one ritual, user two beta brand, and so on. Correct? All right, that's called Cartesian. Using Cartesian, you can create many things. Let's say you are saying join RDD1 and RDD2 where user is equals to 1 and venue equals this, right? Or venue is not equal to this, some kind of that. So what you can do is after Cartesian, on the resultant RDD, you can call the filter method, right? So you can do the where kind of clause, the joining, the left join, right join, using Cartesian and filter. All right. Now another function called fold. Fold is very similar to reduce. It provides a little extra control over initialization. It lets us specify what is going to be the initial value before it starts reducing. You remember in case of reduce function, initially the initial value is always the first value of a partition, right? in the reduce function. First value combined with second value, the resultant is combined with third value, and so on, right? So in case of fold, it lets us define a ground value with which every other value will sync into, or it lets us define a zero value, which is basically the beginning of reduce on every node parallelly. Okay, it basically provides us a little extra control. Let's say you have two partitions of an RDD, first partition having 3 elements, 172, second partition having 476. Okay, so what the fold does is, when we say fold and we provide a function and an initial value, so for initial value is used on both the partitions parallelly, and there first one will be combined with initial value, then 7 will be combined with the resulting value, then 2 will be combined with the resulting value. So 1, 7, 2. There'll be 3 function call here, 3 function calls here. Okay. So you can see that there'll be one extra call. Earlier we were first combining 1 and 7 using reduce, then resulting was being combined with the 2. So there were only 2 function calls here, 2 function calls here, but here now there are 3 function call here, 3 function call here. But it has given us a little bit more control. Okay, and the same initial value will be again initialized on the driver node, and result 1 and result 2 will be combined together. That will be our fourth and fifth calls. Okay, so result 1 will be combined with the initial value, then result 2 will be combined with the initial value. Is it good? This is called fold. The example is, let's say before concatenation, we want to concatenate with underscore. Okay, so first we converted every value into string, because fold, like reduce, returns the same data type as the argument. So then what we did was we created something called concatenate. What concatenate does is it combines the two strings. Okay, and let's say initial value is underscore. So if we have two partitions, one containing 1, 2, 3, 4, 5, second one containing 6, 7, 8, 9, 10, and when we combine these values, what will happen is first partition will combine with underscore, then second partition will combine with underscore, and then overall. Okay, so basically in certain circumstances, this is very useful. I will come back to the real world scenarios when I discuss another function. Okay, so fold is a useful function, but not very useful. Okay, it's just little more useful than reduce. The more useful function is aggregate. Okay, there is one more function. Let me just go ahead and, all right, I think that's for another one. Okay, now there is another function which is far more useful than reduce and fold, which is called aggregate. You can think of aggregate as a really customizable form of reduce function. You remember a reduce function? Reduce function was returning a value which was essentially same data type as the input value. And reduce function was being called to combine all the values of a partition as well as the values coming from different partitions, right? So therefore, there was a need of a more customizable function. Here, first all values of each partitions are merged into initial value, okay, using sequence operation. So aggregate basically is called first with initial value, and then resultant is called with two functions, sequence operation and combination operation. The sequence operation is used while combining all the values of a partition into an initial value. And so uh, so first sequence operation will be called on all the partitions parallelly, and then the resultant of these three will be combined using this combination operation. These are the two functions. First function is this, second function is this that you need to define. Okay. In case of reduce, you are just passing the same function twice, right? All right. So you can imagine that, let's say you have two partitions. These partitions are defined by square values, right? And initial value is the round value. Okay. So before the aggregation starts, we define the initial, we use the initial value. So these values are being merged into the initial value. Okay. Initial value is something that's used to merge all of these. Okay, so here first initial value is combined with the first element, then the resultant is combined with the second element. Similarly here initial value is combined with first element, then initial value is combined with the the resultant is combined with the second element, and so on. Once it has finished combining all the values of a partition on all those functions, then the resultant will be combined using combine the second argument. So first function is being called on each partition while the combination operation is being called on the driver node to combine that. Okay. So let's say we are trying to do the average computation. You remember our problem, average computation? We could not do it in a using a reduce function in a single shot earlier, right? So here we are defining an initial value which has two things. One is called the sum and the other is called the count. Initially both are 0. Now we are saying we are defining a function called sequence which takes a tuple and an initial value, okay, which takes a tuple and a value and it returns a tuple. Okay, so what it's doing is this is initial value, it's adding this value into the initial value. Okay, so every value will be combined to this initial value. All right, now we are defining another function. What will it do is it will combine these values which are resultant of sequence operation. So what does sequence operation does is it will be executed on every node and it will convert each of these numbers into a tuple. How? By adding it to the initial value. So one will be added to the initial value. How? The sum will be added with 1 and count will be increased by 1. So sum will be added by the value and count will increase by 1. Is it clear? So this function, what it will do is it'll take each value from a partition combined to the init. Okay. What does init represent? Init represents the sum and the count of each partition. Right? So this is how init will be called. This is how it will happen. So let's say this is your 0, 0, the tuple. First value will combine here. It will become 1, 1. Then second value, let's some 20 is here. So 20 plus this value and the count will increase. So here we are generating count and sum together and so on. That's what we are doing here. Is it clear to everyone? Everybody? No? Now, a simple question which arises here is, what's the point of using such kind of thing like aggregate? It looks a little too complex. But here the important part to notice is the result of aggregate function is different than the actual data type. Here, the data type of the RDD is integer, while after running sequence operation, it will become a tuple, right? It is generating a tuple. All right. So the value the value of RDD, the data type of RDD is getting changed. While in case of reduce, the return value would be same as the input value. The data type of return value will be same as the input value. Okay. Now we are defining another function whereby we are summing up the sums from all the nodes and then summing up the counts, and we are calling this aggregate. Okay. Is it clear to everyone? You want to execute this function? I'll just give you this copy. Okay. So try to understand step by step. Okay, let me take it in the notepad. I hope you are not zoned out. Okay, so we defined an RDD with 100 records, 100 records from 1 to 100. Okay, we defined a tuple called init. It could be any variable. All right, and then we are defining the sequence operator. Okay, let me just show you what happens if we call sequence operator with init, right? So if we are calling the seq function with init, let's say 10, what will happen is the resultant will be 10 and 1. Okay. Okay. Let's say I'm just showing you, let's say, well, res equals this, correct? Now res is 10, 1. If I again call the sequence function with the result, right, with say 5, what would happen is this value will become 15, and so the sum is increasing, sum is being summed up by the value 5, and count has increased by 1. Okay, so what we are doing is just using the reduce function to do the entire magic. The translation from each value into a tuple we are doing using the reduce function. Okay, so is the sequence, this definition clear? It takes tuple and a value, it returns the tuple added with this value and count the tuple's x value added with this value, and y value, the second value, increased by 1. Okay. Okay, so looks like only Michelle is in the zone. I think everybody had zoned out. Yes, it's actually a more concise way of computing the average. Now we define this function. What it does is it combines two tuples. Tuples representing sum and count. It basically adds sums and adds counts. Okay. All right. So Anil's question is, what if we had 5 partitions? No, you don't need to. You don't need to worry about defining comp function. Comp function essentially sums up the two. This sums up two tuples at a time and will be called again and again. So sequence function will be called again and again until all the values of each partition has merged into the initial value. And this initial value is copied to all the nodes. So initial value 0, 0 will be there on all the nodes in the beginning. Okay. And then using sequence function, every record will be merged into it. Okay. Every record will be merged into it. And then the comp operation will be called. So if you have 100 partition, this comp function will be called 100 times. If you have 1,000 records, sequence function will be called 1,000 times. Okay. Now, once we have defined our comp function, we can call this using this. Okay. So D contains the sum of all the sums and sum of all the counts. Good. Now we can easily do things like divide by D dot underscore 2. Okay, since it's integer, therefore it has given us 50. If we just multiply it by 1.0, it'll give us 50.5. Yes, that's right, Robert. So this function will be called against every record, okay? While this function will be called once sequence has finished the job, okay? Again, the same diagram I'm going to. So this is the sequence operation happening, sequence operation, sequence operation, sequence operation, sequence operation, and this one is a combination of operation, okay? This combo operation is happening here. And this will be also recursive. If there are like 100 values, the result of this one will be combined with second one and so on. Although there's a little mistake here. No, actually this is correct. Sorry, this is correct. All right, does it make sense to you? Please feel free to ask. I can explain it further if you want. Isha, are you with me? Asim, Gaurav, TJ? All right, so looks like TJ is not with me. All right, great, great. All right, all right. So are you guys trying? Gaurav, are you trying to run it? All right, do it. A question from tuple is, sorry, a question from Najib is that one thing, it's not necessary for scalar values, right? No, you can have tuples as well, or you can have anything. A question from Anil, if init is 110 and partitions are 2, then sum will be added to yes, and count will be added to this. Yes, that's right. So if init is that value, then every record will be added to this on both machines. A good question. Let me show you what he means, and it's something very important. Okay, so let's say we have few numbers here. Is it visible, or should I increase the font? All right, and let's say one more. Okay, let's say here I'm drawing a line. Okay, this is partition 1, this is partition 2. Okay, and let's say initially we did our init value as 10, 5. That's the init value where we have provided to the aggregate function. Okay, so this value, init value with tuple will be passed to both machines. Okay, then your function will be called and asked how to combine these two different types, the init value and the argument. That also brings us to the point that the sequence operation that we are sequentially applying, it should take the input as the RDD's data type and the second value as this, and first value's data type should be same as the init value. Okay, so whatever function you are defining as sequence operation, its data type, its first argument should be same as, so data type of first argument should be same as the initial value, and second argument, which is this, should be same as the RDD's data type. Okay. Now this function, when sequence function is called, it will result in what? It will give us 11 and 6. Okay, is it clear why it is 11 and 6? Okay, all right. Okay. Let me explain this part which Najib has asked and Anil has asked. Okay. Okay. So we are increasing the counts by 1 and we are summing up this. That's what we are doing as part of this function. We are increasing the counts by 1 and summing up I with the value of the first value of the tuple. 10 plus 1 and 5 plus plus. Okay. Now these two will be combined together. What will be the result? Quickly. What will be the result? Anybody? 13 and 7. Correct? Similarly, here also, okay, here also these two values will be combined first and the result will be how much quickly? 18 and 6. And then 5 will be combined with this. Yes. 23 plus 7. 23 and 7. Correct? Okay. As per my understanding, this is something I need to confirm. Here, the init value will again be initialized. 10, 5 will again be initialized. And then these will be combined together. Okay. Now this is happening on the driver. This part is happening on the driver. Driver gets these two values, 13, 7 and 23 by 7. So it got two tuples and it need to combine these. So it will first combine the first value with the initial value, right? So it'll become 23, 12, right? Then it will combine these two. What will that be? Yes? Anybody? This is essentially happening. I'll just make it blue. It'll make more sense to put it like a blue because here the combination operation is happening. Okay. All right. Yes, it will be 46 and 19. Good, Michelle and Robert and Najib. Oh yeah, no, actually, Asim's question is, all right. Asim's question is, should this be combined with the initial value? No. The combination operation is called on this array of the resultant of all the nodes, and then the initial value is joined with the combined with the first element, then second elements. All right. Good question. So 12 plus 7 is 19. Got it? You see, because here, while combining things, we are just summing up the two values, underscore 1 plus underscore 1 from both the value, both tuples, you see? Summing up 23 with 23, 12 with 7, and that's it. Similarly here, 10 plus 13, 5 plus 7. Yes. So basically, while partitions are the resultant of partitions are being combined using your combined function, the initial value is here. Right. So actually, this diagram is slightly wrong. The correct diagram was the earlier one. I'll show you which one. The fold one. Okay. You remember this one? Here also, finally, this initial value is again initialized, right? And then these values are combined together. Okay. So similar to fold, here also the same thing would happen. Yes, I think it'll be used for both. I think this diagram here is incomplete. Here, these value also will be combined with the initial value. All right. You can try it out. I would love to try it out. Okay. 1, 2, 5, 8, 10, and 5. Okay, let me see. Let's say we have an array. Well, A equals, and after this we'll take a break. 1, 2, 5, 8, 1, 2, 5, 8, 1, 2, 5, 8. Okay, that's the array. And we are saying sc dot parallelize with two partitions. Okay, and then we are defining an init value of 10, 5. Okay, let me just check if this is correct. Okay, now we are going to call the same function that we called earlier, this one, sequence and this. All right, and then we are saying d equals to, sorry, not RDD, it was a dot aggregate 46 and 19. Did you see that? All right, 46 and 19, it was our hypothesis, and this is what happened here. Okay. All right, so our understanding was correct that even while combining, this is used. Okay, let me just keep this diagram on this slide so that I can refer it back. Okay, Gaurav's question is that what I'm missing here, is we did not get 13.8, but we got 13.7. 13.7. Good. So here, it's not 2 that's getting added to 6. It's just 1 because we are second value in the tuple. Second value in the tuple represents count, right? Because we are tracking two things. By using recursion, we are computing two things. One, total, and other, count. So count is increasing by 1 while total is increasing by that value. So 11 plus 2 while 6 is increased by 7. 6 is increased by 1. Okay. I hope this is clear to everyone. All right. So a question to all. Can everything that is done by reduce can everything that is done by reduce be done by aggregate too? Okay. Can everything that can be that can be done by reduce be done by aggregate. So the answer to the first question is yes. Anything that can be done by reduce can also be done by aggregate. Now, what is your answer to the second question? Can everything that can be done by aggregate be done by reduce? Correct, right? So aggregate is far more powerful than the usual reduce function. It gives us the ability of distributed computing, as well as it gives us ability to customize how things will be combined and how things will be reduced. Okay, so that's a very, in single pass we did the entire thing. We did not require any mapping, or we did not require anything else. All right. All right. Now there are other functions like count by value, which are very easily available functions, so that if you want to just do the frequency analysis like word count, if you want to do the word count, you can use count by value. Okay. The only downside of count by value is it's an action. So on whatever you run count by value, the result will come back to you locally and it might overflow the memory. Okay. Then if you want to just extract the maximum values, maximum n values from RDD, you can use top n. It sorts and gives you n biggest values. Okay. Similarly, we have a function called take ordered. It gives you, it calls take after sorting the data. It sorts the data and then calls take. Meaning, if you want to pick up any small numbers and big numbers or and so on, you can use take ordered. Okay. So take ordered has many variations. First one is you can just pass the number, what you want to, how many records you want after sorting. Meaning, let's say we are saying take ordered 6. It'll give us the smallest 6 numbers from it. Okay, it basically sorts ascending. Then let's say we have another RDD and we would like to take ordered and customize the function of sorting. Okay, thank you so much, Anil. Yes, there is a typing mistake here. Okay, and O is capital. All right, so what you have here is this. It gives you the result in ordered way. All right, this gives you the result in an ordered way. All right, you can pass the function on the basis of which you want to sort and so on. All right, and whether you want to say reverse or ascending, if you want to say ascending, you just say dot on, and if you want to say reverse, you can say reverse. All right, but it's not really required. Easier one will be the sort it and take it. Okay. A question from Robert. Are there real-time use cases of custom RDDs needed? And I assume that you need to give implementation of almost all the mentioned methods we discussed. So these implementations are, okay, now I got your question. So question from Robert is, do you think that we would require a custom RDD? No, generally not. And And RDD does let you extend the RDD. And in case you are extending, you can provide extra methods on RDD. Okay. Like for example, somebody created data frame, which is an RDD, just that it has column definitions as well. Okay. So in that case, is they extended RDD. In case, let's say you want to represent a graph or a complex structure as a parallelized collection, in those cases, you might have to extend RDD. Okay. Generally, it's not required. It's a very good question. All right. Now, all right, let's take a break here, and after the break, we will talk about these few functions. All right. Break for 10 minutes, back by 9:57 p.m. IST. Hi, everyone. I'm back. So can we start now? Hi, Anil, Gaurav, Gerald, Isha, Michelle, Najib, Robert, TJ. Can we start now? All right. So let's start from where we left. All right. So let's say we want to compute something on the RDD, but we do not want to generate another RDD, right? Let's say there is an RDD and we want that RDD to be saved to database. Okay. In those cases, we could use a method called for each. For each is called on every element of RDD, but the result is not saved into another RDD. The function that you pass to for each does not have to return any value, or I should say, should not return any value. Okay, so you can call, you can create your function which takes the each element, this data type of the element has to be same as the data type of your RDD. This is the RDD here, and then for each is being called and we're passing a function. Here it just println and it's printing something. But in reality, it could be anything. Similar to for each, we have another function called for each partition. In case of saving to database, A better and more optimized version would be to use for each partition. Okay, why? Because for each part, instead of creating a database connection for every record, we can create the connection for every partition, right? If you have map partition, you can iterate over the records in that partition and create during initialization a single database connection. All right. The difference from for each is if you use for each, if you don't expect any result, for example, saving to database, printing the records, or doing something else. For each is just action. For each is an action while map is a transformation, meaning when you call map, after that we need to call action such as collect or take or save as text file, right? While for each is an action and it would instantaneously happen. Similar to for each, we have for each partition. It applies the function f passed to for each partition on every partition of this RDD. Okay, so let's say we defined a function called partition sum, which takes an iterator and it's computing the summation of RDD. And it just prints the summation of each partition. Okay, so we are saying parallelize and creating 4 partition by passing the second argument to parallelize as 4, and then we are saying for each partition and passing this function called partition sum, so every partition's summation will be called. Okay, so these were some methods of basic RDD. All right, the second thing which I would like to discuss now is the key value RDD. Okay, the key value RDD. Just give me a second. I think no, not this one. This one. All right. Okay, so we learned quite a few things today. We learned about how to compute sample of an RDD programmatically by ourselves as well as using a function called sample. We also learned map partitions. We also learned various set-based operations. And we also learned sorting of an RDD and so on. Okay. So utilizing all these things, we can create very sophisticated computationally intensive programs in a distributed fashion. You can divide the computing on multiple nodes very easily, okay, using RDD kind of a convention, using the convention such as RDD, which looks like an array to us, and but under the hood, it is distributed. Just that while operating on this array or RDD, while operating on an RDD, we need to be careful. If we need to, let's say, sequentially operate an RDD, we need to think about why do we need to operate sequentially. Okay, because we are very much used to our functional programming, our what do you say, our sequential programming like for loop, go to loops, go to conditions, and random if else and so on. Instead, when we are operating on RDD, we have to think like a database administrator or a relational database person who need to think about things in terms of translation of set-based records, or you can say set-based approach. Okay, how do I translate this into this? How do I filter this into this? How do I order? How do I group by, and so on? That's how we need to look at an RDD like a database table instead of just thinking about looping over it, thinking about jumping at random place into a table. We think in terms of group by, select statements, and so on, right? All right. Now there is another Although you can keep anything inside an RDD, but the key value RDD has a special place. If you put a tuple instead of any other object, if you put a tuple, by default, the Spark will think that you are trying to do a key value RDD, key value operations. The first value of the tuple becomes the key. There's a data type called pair RDD, and that's basically a specialized RDD. Okay, so under the hood, Spark tries to provide you various kinds of operations on key value RDDs. Okay, so all you have to do is translate your RDD into a tuple, and that's it. Then you can apply key value kind of functions. Okay, so imagine that we have our RDD containing key as banana and the count and so on. You see, it's a tuple RDD. This is essentially like this. Okay, so so you can keep any kind of data in RDD, but having tuples is quite useful. For example, pair RDD, you can call things like reduce by key or sort by key, and you can do joins based on the key. Okay, key value RDD containing tuples with the first value, first member as the key. This is the key, and rest is value. Okay, now in Scala, pair is defined as x comma y, also known as tuple. A tuple is immutable sequence of objects which we have studied, and you can convert a list into tuple and vice versa. All right. So imagine that you have a list of tuples like here. We have defined the list of tuples like this: 1, 2, 1, 3, 2, 4, and 1, 6. And we're converting this local data, data, which is a list of tuples, into an RDD. Now this one will be a RDD having key value pairs. Okay. All right. Now there are various specialized functions that you can call on the RDDs, which are pair RDDs or key value RDDs, such as reduce by key. We have studied reduce, but reduce by key is similar to reduce, but the reduce happens on every unique key. Okay, so it groups the elements of an RDD based on the key, and key is the first variable of the tuple. It first groups the element of RDD based on the key and then reduces all the values of that key, all the values of each key, using the function that you have passed. Okay, so it's like first calling group by key, and then for each one we are calling a map function, and on values we are reducing it. That's what reduce by key is, just that it is very much distributed. Okay, so reduce by key is equivalent of a combination of map and reduce of Hadoop, and reduce by key essentially is like group by. We provide the aggregator function as argument, and the aggregator function, the whatever function we are passing, it should be commutative and associative. Okay, so we are parallelizing the RDD and then calling the reduce by key with the reduce function as argument, and then we are collecting the result and printing it. All right, so you can see that reduce by key has resulted in the frequencies of the members. Okay, you can see, so one has occurred, one, and for each of this one we are summing up these values. So 1, 2 plus 3 is 5, 5 plus 6 is 11, and 2 is 4. You can see that. Is it clear to everyone? Any questions on this? Let me give you a more detailed example. Imagine that your RDD is like this: 1 2 1 3 2 4 and 1 6. So first, when the grouping would happen, it would result in 1 comma 2 3 6 and 2 comma 4. So after grouping, there are two elements, and then the reduce will happen. The reduce will first reduce 2 and 3 into 5, and then 5 and 6 to 11, right? Because our reduce function was just summing up a plus b, correct? Let's take a look at the word frequencies. Okay, imagine that you are given a huge file and you want to compute the unique counts of each word. Counts of each unique word is what you plan to do. In that case, you can use this approach to find the unique words in a text file and then find how many times each word has occurred. That's what does the that's what uh, this function does. All right. Yes, we have already used this in the word count. Imagine that you have the sa re re saga kind of input text. Okay, and we want to find out the frequencies of the words, which means we want to say ga has occurred once, re has occurred twice, and sa has occurred twice. And this input text contains lines of words. First line is containing 3 words, second line is containing 2 words, and we need to compute the frequency of such text file. Okay, so what would happen? How would we do that? How would we compute the word frequencies? So first of all, we would be loading the data as a RDD using sc.txt file. What does sc.txt file do? It creates an RDD having each line as a record. So the length of RDD will be equal to the total number of lines in the text file, right? So the first thing what would happen is here what we're trying to do is we are doing flat map. What does flat map do? Flat map here is taking a function which splits each line into array. Okay, so sa re re will get converted into 3 records. Similarly, the second line, the second record will get converted into 2 records, which means after flat map, 2 records will be converted into 5 records. When we loaded this text file, this was 1 record and this was another record, right? And when we split each of this using flat map, this will this will yield 3 records, or this will produce 3 records, and this will produce 2 records. Okay, then we are calling a function called map. This will be called against every record. The same depiction I'm trying to do as a diagram. So this one broke down it into 1 record. Okay, imagine that records are vertical here. And then using map, what we did was we converted into lowercase. We converted into lowercase and said 1. So sa will become sa comma 1. This is 1 tuple, another tuple, another tuple, and so on. Now, once we are done with this, this will be a pair RDD. This is a key value pair RDD. And then we can call things like reduce by key with the aggregator function here. Now, once we call that, what would happen is when we say reduce by key, and this is a function, first these things will be grouped. So it'll be ga 1, re 1, 1, sa 1, 1. And then when we call reduce, it'll reduce these things, the values of each key using this function applied on these values exactly the way we were applying reduce function earlier, recursively again and again until a single value is left. Okay, so this is how we computed the word count. Okay, once this is done, we can take the result and save it. Save as text file. Okay, save as text file would be working fine now. Do you want to give it a try? Or it's okay because you all have already done it? Okay, you can give it a try. I think a better idea would be to give a try to the next example. This one is already clear to us. Okay, all right. Now, the word count is something which we all do all the time, and I think this is a very overused example. All right. Now let's say that we are given the temperature of all the cities on various dates. For example, we're given the comma separated file here. The first value is 20, comma, the city name, and then the date. Okay. So basically we're given this text file containing comma separated values. And what we would like to do is we would like to compute the max temperature of every city. For example, NYC over all durations, over all dates, it has got the maximum temperature of 26, while Bangalore has 23 and Seattle is 25. It has no relation with the actual temperature. It's a dummy data. So do not, uh, you know, just do not take any judgmental call on this. Okay, so for every city we are trying to compute the max temperature. So NYC is 26 and so on. You can see that. How would we do that? Anybody? It's a plain text file or CSV file containing all the records. Yes. So how? Okay, so TJ is suggesting that the map function will generate the city as the key and temperature as the value. We don't really need the date. That's right, Michelle. But why do we need filter? Filter will get only one value at a time, one record at a time, not all records at a time. It's only the reduce function or map partition function that gets the more than one records. Map gets only one, flat map gets one record, filter get one record, and so on. Okay, thank you, TJ. So what we will do here is we will first convert this into key values, right? Here there's a need of shuffling because we are trying to find out the max temperature, right? One way could have been that we take New York City, then scan through the entire text and find the max value, then pick up another one and keep on going like that. That could have been um, very inefficient, right? Instead, if we do a group by, okay, and then do the max, right? How would we do it in SQL, right? How we would do it in SQL? We'll group by based on a column and then do the max, right? Anil, if you think about your suggestion to in terms of SQL, do you think that's applicable? Would you use that approach too? Can we use where clause? Can we use where clause to find the max temperature per city? No. All right. It's an important aspect. What we are talking is again and again, when you think about either Hadoop's MapReduce or Spark's way of doing computation, you always think in terms of a database table. Okay. So here we are trying to compute this. It's pretty easy. One is let's load the data. Let's load the data first into an RDD. Let me try this. Does it work? First of all, let's take a look at the data. Okay, let's take a look at the data. I'm opening the Hue. Okay, you can also try in parallel. I'm opening Hue, and in the file browser, the data is lying in /data, meaning the top level folder, and then in the Spark folder, and then temps.csv. Okay, so we go to top level folder /data /Spark. Where is the Spark? Here. Do you see, where was that? Do you see temps data anywhere? Here. It's a very small file. Okay. All right. So it has data, comma, space, then another value, comma, space, another value. All right. Now let's load this as a RDD. Okay. So we created a variable called text RDD containing this. Okay. If you have a doubt about what does it have, let's take a look at only one element. Okay. So you can see that it's basically a single string. It's basically a single string. Don't worry about the data type here. It's an array of string. Okay. res17 is an array. Okay. If I see 0, the 0th value is the whole string. All right, is that clear? Then we define a function called clean record. Okay, what does clean record do? Clean record takes a string as argument, then split the line, whatever is the argument, by comma, and then trims the two values. Okay, it converts the first value by trimming. Trimming means removing the /n or space from the beginning and end of the string. And then it also converts the second value into a 0th value into a number after splitting, and first value gets in the key. So NYC will become the key. Let's just test it. Okay, let me test it with res170 or with this string. Okay, so we say clean record. Okay, and we pass the string. You can see that it has returned a tuple. It has returned a tuple having a string and the integer. Okay, so I just defined a function called clean record, and then let me also give you the function definitions. Okay, all right. So this records already after mapping. Let's take a look at, say, 2 records. How does it look? Or 1 record. You can see that it has done the job. If we say 2 here, you can see it's working fine, right? Now, then we define a reduce function. Okay? In the first line here, we define max. What does max do? It returns B if B is greater than A, otherwise it returns A. The A and B are the integer arguments to the max. Okay, please notice that the max function which we have defined takes only 2 values, not an array. Okay, When we do call this max, it has given us the results. Okay, it has given us the result, and this is wrong. All right. Now here I'm defining. Let me again define and give you the method. Okay, so resultant is the shuffled RDD. Okay, then on the resultant, I'm calling the collect method. So you see that it has computed the max temperature of the cities. All right, is it clear to everyone? Okay, so we loaded the text file as an RDD, basically converted this, then using clean record, we created this kind of a structure. Then using reduce by key, we first group the data. You can see we group the data and then reduce the data based on our max function. All right. So that was pretty much the basics of key value RDD. I'm going to go into more details now. All right. We'll talk about joins and other functions. Is everybody able to get it done? If somebody is stuck, let me know. Anil, Asim, Gaurav, Gerald, Isha, Michelle, Najib, Robert, TJ. So if you have a question, you can let me know. If you're stuck, let me know. Wonderful, wonderful. Okay. On key value RDDs, we have just used a function called reduce by key, but there are quite a few functions available on the key value RDD. Okay, so is everybody able to execute? TJ, I did not see your response. All right, wonderful, wonderful. Great, great. All right, so there are quite a few functions on the key value RDD. An easier way to explore these functions is by just looking at the documentation. Okay, but I'll just take you quickly through the important functions so that we all are comfortable with most of the functions. So there's a function called keys, which converts a tuple into tuple RDD into a normal RDD and gives you only the keys out of it. For example, here 1, 1 and 3 is returned. All right. Okay. The second one is values, just like keys, but this time it would basically give us the value of each tuple. It's a quick, handy method. Can you do it otherwise? Can anybody suggest any other alternative to values in keys? Yes. If the values function is not provided, can you do it otherwise? How would you achieve the same thing what values achieve? Correct, correct, Najib and Robert. Map function, the key value, if we just run a map on this, okay, I'll show you. So most of these things can be achieved easily using our basic mechanisms. Okay, so for example, this one. So this is the values, and let's say I'm defining a parallelize function here. Okay, so let's say, so M is an RDD, and I could say map and only return only the, okay, so I can show you that it will give us this, right? It's actually pretty simple. Similarly, for keys, if you ask me, I can actually achieve the same thing easily in a single statement, right? We could say map, and we could return say underscore and one, or we can say collect. See? All right. So we can achieve a lot of things using map function and the basics of it. Values. Similarly, group by keys. Group by key is another function which basically groups the data, but it doesn't make much sense because if you group the data and then you either call a map or flat map on it. Okay, so I'll show you what does it mean. Okay, so here, if let's say we have done the grouping, okay, so after grouping, we first grouped it. So RDD1 contains the result, right? So if I say take one, it is giving us compact buffer, okay? Now we can write things like RDD1 dot map, okay? And it'll basically do the, in the map, we can further do the other work, or we can do a reduce by key instead of group by key. All right. So now next question is, what will be the result of the following? Quickly, anybody? So there are set functions. Okay, we'll talk about set functions soon. So first we parallelize the results. This is, I think this was supposed to be removed. All right, this is supposed to be moved because this is yeah, this is a Python code. All right, no worries. Okay, now similar to aggregate operation on an RDD, the very important function we have on key value pairs is combine by key. Okay, combine by key is a really sophisticated version of reduce by key, right? The way we had aggregate, sophisticated version of reduce, similar to that, we have combined by key, a sophisticated version of reduce by key. It goes one step further than our usual. Okay, it goes one step further than our usual aggregate function. So combine by key takes three arguments: create combiner, merge values, and merge combiners, and optionally number of partitions, because it is going to involve shuffling, and shuffling is a great time for creating new set of partitions. But important part here is it takes three functions: create, merge, and merge combiners. Okay, I'll show you what does it mean. Okay, instead of taking an init value, it lets you call a function instead of static value. It lets you define a function which is supposed to create the 0th value. Okay, so that's basically different from aggregate. So create combiner. So combine by key turns an RDD of key and value type into a result of key and C type, say. Okay, so you have keys which could be same, right? And the V is be getting converted into C. Here, let's say it was string and we are converting it to, say, a number, right? So reduce basically cannot handle a situation where the return type and the value that's being processed are of different data type. For example, in case of reduce, we summed up numbers. So input was numbers and output was numbers. Similarly, in other cases, reduce can only handle the same data type. Okay. To avoid that, to avoid that, to 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 have a better function, we have the combine by key. All right. A question from Michelle. The number of partition equals none isn't doing nothing. It is actually a useful function, and we can utilize that function. Okay. It's an optimization step. It's an optimization step. Let's say you are running filter, and while combining, you want to also reduce number of uh, partitions. At that time, you can define how many partitions do you want. All right. Now, here, most important part is that we need to define three functions. Okay. We need to define three functions, and basically, it is similar to what we did in aggregate. Here we are just defining an initial value using create combiner. Okay, so I had a great diagram here. Yeah. All right, let me take this example. This is a very important example. Here we are saying my RDD and we are defining a list of numbers. Okay, we are defining a list of numbers and we're converting it into a single key value. Okay, by calling map. So the resultant of this one will be like this. Okay, so my RDD, if you say collect on this, how does it look? It looks like a key value pair. You can see it's it's having so many records, right? 5 records. The keys are same for it. Okay, because this function is operated on key value pairs. Okay, so first of all, we converted this into a tuple, into a key value pair or tuple RDD. Then we define something called create combiner CC. It's our own function. What it does is it converts the value into the resulting data type. It's the one that's creating the initial value. The init value that was static in aggregate is basically defining that. Then MV means merge value. If there are two results of CC, how will a value from this RDD gets merged to the value which is generated by CC. CC is going to generate the initial value, and how will each value get merged to initial value, that's defined by MV. Then MC is merging two values from different partitions. Okay, the result of MV will be merged by MC from each partitions. That's what is happening here. And then we're calling combine by key. Okay, imagine here what we want to achieve is we want to concatenate this into a string. We want to concatenate these values into a string. Okay, let's say we have this and we want to concatenate this into a string. This one, initial one, would have a tuple like this. Okay, we want to concatenate all the values for each key into a string. Right now these are numbers, right? If we use reduce function, we can't directly use reduce function. Why? Because reduce will always return the same data type as the actual value. One thing we could do is convert each value into a string and then call reduce function. But that wouldn't give us a lot of flexibility. That's why we have defined this. What CC does is nothing. Whatever number you give as argument, whatever number you give as argument, it converts that into a string. Okay. And then the second function basically combines a number and a string. Okay. It combines a number and a string. And third function basically combines two strings. Then fourth function, there is no fourth function. This one is essentially being called on that is calling all these functions in that order. All right, now let's take a look at it again. So 1, 2, 3 is getting combined into 1, 3, 2, 3. Okay, that's what is combined by key is doing. Sounds simple. So we have, let's say, two partition. One is having 1 and 2, and second one is having 3. So first CC will be called. Okay, now number is represented by blue, and this color is green probably. So number 1 is getting converted into string, right? Similarly, parallelly on another partition, CC will be called and 3 will be converted into string. Similarly, 2, once that is done, 2 will be merged with 1 using this function called mv, right? And this mv function, what it does is it first convert y into a string and then calls this. Okay, and therefore you'll get 1, 2, 1, 2 dot string. So we get 1, 2. Okay, so CC is getting called only once, not twice. Why? Because it is called only during initialization of this string. Okay, the things like you want to create a string object once for every partition, that can be done using CC, the create combiner function. This function can create a string to which, or maybe an array to which we can append to things, so that that initialization doesn't happen on every merge. And once mv function has concatenated one string and 2 as number, we've got a string output. Now a string and a string has to be combined together, and we could combine only a string and a number. Two strings have to be combined together, and for that MC is used. Okay, MC had generated 1, 2, 3. Does it make sense to you? So we define CC function to initialize the init value, right? Instead of statically defining init value, CC function is defining the initial value. Now, the MV is basically combining this string with the number. You can see y.to string. A question from Robert. The output of CC is passed to MV atomically. Yes. Internally, yes. Automatically, actually, not atomically. So basically, if there are 5 numbers here, so 2 will be merged with 1. The resultant will be then again combined again and again. All right. Just like we did earlier. Had there been, like, say 4 here, 4 will be again using MV, that will be combined. All right. Okay, so it's basically more sophisticated and more customizable version of aggregate. A question from Najib is that CC is not used in the last step. Correct. Why? Because CC takes integer as argument. CC takes this rectangle as argument, the same as RDD, and converts it into the data type of the output. Okay, there are two data types. One is input data type, the blue one, and there is another data type called green one, right? So CC converts one blue into green, Okay, one blue into green. Then MV combines blue with green, while MC combines two greens. Okay, blue means input data type and green means output data type. Okay, I know it's little this is something not is not generally discussed in the distributed computing, but this is actually the most powerful function instead of reduce. We are quite quite used to using map and reduce, but combine by key and aggregate are the two very powerful functions. All right. All right. I have no clue. All right. Okay. So essentially, CC is called once to create the zeroth value. Then other values are being combined to zeroth value using MV. And then each partition is getting merged using MC. Okay. But honestly, when I was actually starting with the whole thing, it took me a while to figure it out that, yeah, this is how it works. All right. So feel free to ask questions if you have any. I know you have questions. So Gaurav's question is, so the output for this example would be 1, 2, 3, which is a string, not the integer. That's right. Anil, Asim, Gaurav, Gerald, Michelle, Najib, Robert, TJ. I know there are questions. Feel free to ask. A question from Michelle. Why would you use aggregate versus combine by key? Combine by key is valid for RDD having tuple or pair RDD, while the aggregate is only for normal RDDs. Good point, Gaurav. So he meant to say that there should be a space, and yes. So we should have put a space here because, and he's right. So the output would be 1, 2 space 3. Let's see. Did that happen? Did that happen? Okay, let me try. All right. Okay, so now let me try this one. All right. So you can see that you are right. Okay. So if you take a look at here, the RDD that we created, where is that RDD that we created? All right. So you can see that it has, I think, how many partition did it have? My RDD dot partitions, my RDD dot collect. So I see it has only one partition. Okay, so I think a better thing to do would be have multiple partitions. Okay, so you are right in that sense that when we call this function, it's basically x and 1 are close together while 4 and 5 are also close. Okay. All right, this is very unusual and interesting. I see. All right. Yeah, so you can experiment with it. You can experiment with it and you'll get the answers. Okay. Try different things like in AMV, try concatenating it with, say, colon. Here, try concatenating with comma and then see the result, what happens, and you'll get a clear answer. Okay. So let's say here, the code is a little different. If you want the whole code, I'll just paste it. All right. So you can see that here, when value is combined, after this, it's 3. All right. So you can give it a try and see what happens. All right. Okay, so here is a question for you. Let's say there's a function called cc which returns the square brackets around the value. Okay, basically concatenating these values, and then we have mv which returns the value like this. It's actually in Python, so we can ignore this question. Ignore this, I think. Yeah. All right. All right. So similar to sort by function, we have sort by key. It takes ascending or ascending true as the argument. By default, ascending is true. And number of partitions by default is current set of partitions. As in, after we run sort by key, the resulting RDD would have same number of partitions as the input one. Okay. So we can use sort by key to order a pair RDD quickly based on the key. All right. And all right. Then we have another function called subtract by key. Subtract by key is similar to subtract method. So it returns all the pairs which are not there in the other one. For example, here, let's say there is an RDD containing A1, B4, B5, and A2, and you want to subtract the second RDD, which is having A3 and C none, right? So A will be removed from the first one. So A is gone, A is gone, you're left with B4 and B5. So that's what is the result. All right. So subtract by key is another. Now, an important function called join. You can join an RDD with another RDD based on the key. All right. It returns basically another RDD containing all the records whose keys are matching in both. So it returns an RDD containing all pairs of element with matching keys in the self in this RDD and the other. Okay, this means the RDD on which we are calling the join method, and the other means the RDD which you are passing as the argument. Okay, so each pair of element will be returned like this. So key, comma, v1, comma, v2, and so on, right? So basically, v1 is from first RDD, v2 is from second RDD for the same key. That's what the join does. All right, let's take a look. Let's take a look. These are important functions. So first we define an RDD here called X, and then we defined another RDD. Sorry. Okay, you can also do that. I'm just copy pasting it both the places in the chat and in here. Okay, so we define two RDDs, X and Y, and when we do X join this, and here you can see that it had joined the two records. Okay, so A12, A13, A12, A13, A1 from here, 2 from here. Okay, A1 from here, 3 from here, and so on. The values that are not existing in other one are removed. Is it clear? All right. Similar to databases, we have left outer join and right outer join. Left outer means all the values from the left will be there in the result, irrespective of whether the key is existing in the right one or not. Here, since the key like C and D did not exist in either, they were removed. Only the keys that existed in both are kept in the output, right? So in case of, let's say this, it has A and B and Y is only having A. So when we say X left outer join Y, A and B will remain in the output, and for the value here, there'll be a none. Okay. So here you can see that what we are trying to do is we are parallelizing two RDDs, X and Y. Okay. So we have one RDD and another RDD. This is one key value RDD. This is another key value RDD. We are doing a left outer join. This dot join this. Okay. This dot left outer join this. That's what we are doing. This is the self. This is the other. So when we say left outer, what will happen? One will be there in the output. Two will be there in the output, but three won't be there, right? So three will be none. Okay, is this diagram clear? What does it mean by left outer join? Okay, the same convention is there in the databases. When you're joining two database tables, the same convention is there. Okay, it's quite useful. It's quite useful. Let's say we want to compute what are the records which are existing in left but are not existing in the right. Okay, only those records which are existing in the left and not in right. How would you do that? After doing left outer, we can apply a filter saying whichever values are none, keep those in the output, right? So those way that way you can compute the intersections, minus or subtract using left outer join or left kind of operation. Similarly, we have right outer join in which all the values from the right will be there in the output, irrespective of whether there is a value on the left or not. If there's no value corresponding to a key from right, that will be marked as none. For example, 3 does not exist on the left hand side. Okay, therefore, or yeah, all right. What's happening here? 1 Sandeep, 2 Shravani, 1 Ryan, 3 Giri. So when we are saying right outer join, so we want 1 and 3 in the output. Yes, 1 and 3 in the output. This is supposed to be 3, sorry. This is supposed to be 3. Okay, so let me just mark it here. This is supposed to be 3. All right, I think a better thing would be to just leave a comment here. Okay, All right. So similar to this, we have a very useful function called co-group. Co-group is basically grouping and joining together. Okay. So basically here what will happen is, let's say this is the input. So it'll first be joined and then grouped. Okay. So you can see that A, 1, comma, 2 and 3. So first it is grouped, then it is joined. So this side will be grouped together, 2 and 3 will come together, and then these will be joined. So 1, comma, 2, comma, 3. And then similarly for the second one, it'll be this. Okay. So co-group is essentially first group by and then join. All right. All right. In the same way, we can call the other methods. Okay, so sometimes you may want to use count by key. Let's say you want to do the word count quickly, you can use count by key, but count by key essentially is a action, therefore it's kind of useless in many circumstances. Okay, because it will bring down all the data to the local machine, and which is not what we are using it for. There's another function called lookup by key. We can use lookup by key to look up a particular string or a number or an object in the whole RDD. So this is what is known as lookup by key. Okay, so you can use lookup by key to quickly look up, right? Otherwise, you could also use filter, right? Filter function for the same thing. But the downside of filter is, even if one filter function finds a value, it keeps on going ahead, and therefore it's not a very efficient way of looking up something. All right. So lookup is efficient filter in case we are just looking for one value. All right. That's pretty much about more transformations on an RDD. Okay. All right. So I would request everybody that you mm, so I would request everybody to take a look at CloudxLab website. Okay. Under my courses, I would strongly request all of you to finish this exercise, this particular one. Okay. There is an exercise called writing a Spark application. Okay. So all of you are now ready for writing Spark application. So please go through it. I have written it in a comprehensive manner. So it's a 16 pages one. Last three ones are most important one. This is probably, this last one is the most important exercise. Okay. The last 16th one is the most important exercise. So please go through this, try to execute all of this, and then in the next session, we should be able to discuss this. Okay? So all of you, please attempt this, because what would happen is it would ask you to install many things. And if we spend time next week to do this, it'll be impossible during the session. A question from Robert. So it is on local machine. So yes, I'll explain to you why. So even though everything can be achieved on CloudxLab, but since when you go to organizations, you generally have a desktop and a cluster, right? Therefore, it's very important to know how we do the coding in the organization. Generally, what will happen is you will set up your desktop with a very rich, powerful editor like Eclipse or Scala IDE for Scala computing. If you are writing a code of some more than 10-15 lines, you would require a sophisticated ID, and Eclipse is a good for that. Okay, and generally in organizations, people would expect you to know that the Eclipse is a place where people code in Scala ID, in case of Scala. Okay, so Scala ID is what you have to install. Scala ID is nothing but Eclipse plus Scala, Scala's plugin in Eclipse. Okay, so this tutorial is a nice tutorial on for Windows, and it will be quite useful to you. Okay, it'll be quite useful to you, and you should be able to install everything, because there's a lot of things, like for example, Scala ID need to be installed and other things. Even though everything was possible with CloudxLab, but this is something which people wanted. People wanted to know that how to set up the dev machines in case of organizations, right? That's why I have created this entire practice, even though entire thing can be easily done using our web console or our lab. All right. A question from Gaurav: anything to look out for when installing on Mac? Actually, the installation on Mac is far more easier than this. All right. So you will know what to do if you just follow the same tutorial. All right. All the documents that are needed in this case, I have referred them and also shown here in this case. All right. I have also demonstrated entire thing. I didn't have Windows, so I bought a Windows machine for this, and it is quite useful to many users. Okay. So please go through the Spark applications so that we can have a meaningful discussion next week. I look forward to see you next week. And the assignment to you is, first finish the writing Spark application. If you don't like reading too much, just jump to the 16th one, and then and then so you just jump to the 16th one here, the 16th one here. Okay, in writing Spark applications, and then we can quickly you can quickly go with the video. Video is around 30 minutes or so, but it's quite condensed video. Not this, and it's just five 5 minutes. No, it's wrong. I see there's something wrong. No, it was 15 minutes. Not 15 minutes, it was 30 minutes. Okay, let me take a look at it. This is something seriously wrong. I did not notice it. I think we have linked a wrong video here. Okay, never mind. So I'll fix it, and you can do it after like 1 hour or so. So I'll fix this and we'll get it done. All right. Thank you, everyone. We are 8 minutes over our usual time. I look forward to see you next session. Please feel free. Please finish all the self-paced course parallelly while we are discussing all of this, and try to attempt the exercises. Okay, and let me know if you're stuck anywhere. Thank you, Anil. Thank you, Asim. Thank you, Gaurav. Thank you, Gerald. Thank you, Michelle. Thank you, Najib. Thank you, Robert. And thank you, TG. Okay, I look forward to see you next session. Feel free to reach out if you are stuck anywhere. Bye bye. Have a good day.